We're building these incredible AI models that can write poetry, that can code, that can pretty much ace medical exams. But there is a huge fundamental mystery at the heart of all of it. We don't really know how they think. We give them a question, we get an answer. But that whole process in the middle, it's basically a black box, just filled with billions and billions of numbers. Today, we're going to try and pry that box open.
So what is actually going on inside an AI's quote-unquote mind? And listen, this is way more than just a philosophical question. If we want to make sure these incredibly powerful systems are safe, that they're not biased, and that they're actually aligned with what we want them to do, we have to understand their internal logic. This is the central challenge for a whole field of study called mechanistic interpretability.
So here's our game plan. First, we're going to dig into why AI is such a black box in the first place. Then we'll look at a really clever tool designed to read its mind. After that, we'll see where the cracks started to show, the promise versus the reality. And finally, we'll look at the next generation of this tech that's pushing everything forward.
All right, so let's start with the big problem. You might be thinking, why can't we just zoom in on one single neuron in the AI's brain and see what it's thinking? I mean, it seems like it should be that simple, right? Well, it turns out the internal language these models use is a whole lot messier than that.
The core issue has this very technical-sounding name, polysumanticity. But the idea is actually pretty simple. It means one single neuron can be a total jumble of completely unrelated ideas. For example, researchers found a real neuron in a language model that would light up for academic citations, for code about HTTP requests, and for Korean text. I mean, what do those three things have in common? Absolutely nothing. It's like trying to understand a sentence where one word could mean 5 different things all at once. It's just chaos.
So why on earth would a model do this? Well, the leading theory is something called superposition. The basic idea is that the AI has learned way more concepts or features about the world than it has neurons to store them in. So to be super efficient, it starts cramming multiple unrelated concepts into the same neuron, overlapping them in this kind of compressed mathematical mush.
This diagram here just nails the concept. Imagine, up at the top, this perfect, idealized world where every single concept, cat, dog, Golden Gate Bridge, each gets its own shiny neuron. Clean, simple. But in reality, what we actually get is the network at the bottom. The model squishes that huge, ideal network down into the smaller one we can actually observe. And so the grand challenge for researchers is to reverse that process, to take those jumbled neurons and unpack them to find the original, clean concepts hidden inside.
And that brings us to the hero of our story, a tool designed to do exactly that. Let's talk about a technology with an incredible amount of promise called Sparse Autoencoders, or SAEs for short. Researcher Nanda gave what I think is the perfect analogy. He said, an SAE is like an MRI for an AI's brain. It looks at all the messy, overlapping brainwaves of the model's activity and tries to translate them into a nice, clean list of concepts. So instead of seeing just a bunch of noise, you get a clear readout that says, aha, the model is thinking about bridges in San Francisco right now.
So how does this magic trick actually work? Well, as you can see, it's really a 3-step process. First, an encoder takes those messy neuron signals and blows them up, mapping them to a much, much larger list of potential features. Step 2 is sparsity. This is key. It basically applies a penalty, forcing the model to only use a tiny handful of those features at any one time. Then, in the final step, the decoder has to try and rebuild the original messy signal using only that small, sparse set of features. If it can do it successfully, congratulations! You've just isolated the true concepts the model was thinking about.
And in the early days, wow, the results were just mind-blowing. Researchers used these on a tiny model and discovered it had secretly taught itself the concept of base64 encoding. They created Golden Gate Claude, a version of the AI where if you activated just one feature, it would become completely obsessed with the Golden Gate Bridge. In competitions to find hidden dangers in models, the teams using SAEs didn't just win, they dominated. And more recently, they've been used on big models like Claude 3 Sonnet to find features related to really important safety issues like deception and bias. The hype was absolutely real.
But as it so often goes in science, that initial breakthrough was really just the beginning of the story. The more researchers actually used these first-generation SAEs, the more they started to find some pretty fundamental flaws. The cracks started to show. It turned out the features the SAEs found weren't always perfectly precise, and just making things sparse didn't automatically make them understandable. There was a weird problem called shrinkage, which meant the tool was constantly underestimating how important a feature was. But maybe most worrying of all,
researchers realized the SAEs were just completely missing some concepts that were definitely hiding in the network.
But the most sneaky and critical problem of all was something they called feature absorption. Okay, stick with me here. Let's say a model has a feature for a general idea, like words that start with the letter S, and it also has a really specific feature for the word short. Logically, when the model sees the word short, both of those features should fire, right? But an SAA learns a kind of cheat.
And here's why it cheats. Remember, the SAE is optimized for one thing above all else: sparsity. It's built to use as few features as it possibly can. So instead of activating two separate features, starts with S and short, it's way more efficient to just create a single corrupted feature for short that sort of absorbs the meaning of starts with S into it. It gets to fire just one feature instead of two, which looks more sparse, but it makes the features totally unreliable. Now, a realization like that could have been a dead end for the whole field, but instead, it kicked off this incredible new wave of innovation, leading to a whole next generation of tools designed specifically to fix these problems.
The big light bulb moment was a total shift in focus. You see, the original SAEs on the left, they were analyzing the static state of the neurons, what they looked like in a snapshot. But the next-gen solutions on the right, they focus on the model's function, not what the neurons are, but what they do. They separate the decision of which feature is active from how strong it is, and this led to totally new designs.
And this thinking gave us a brand new toolkit. First, you have gated SAEs, which solve that shrinkage problem by having one part decide if a feature is there and a second part decide how strong it is. Then came transcoders, which changed the goal entirely from just looking at neurons to actually predicting what a piece of the model was about to do. And the latest evolution, skip transcoders, adds a really simple but brilliant tweak to the architecture that just boosts performance like crazy.
And hey, you don't have to take my word for it. The results really do speak for themselves. On this chart, the goal is to be in the top left corner. That means you've got high interpretability with very little damage to the model's performance. You can see the original SAEs, those green dots, they're kind of stuck down in the bottom right. But the new skip transcoders in orange, they are exactly where you want to be. They are just flat out better on both metrics. It's a true leap forward, with basically no downside.
All of this brings us to a final, pretty tantalizing question. The progress here is happening incredibly fast. We're really moving from what felt like blurry X-rays of an AI's mind to something more like a high-resolution MRI. So let's imagine for a second that we succeed. If we build a tool that can perfectly and reliably read an AI's thoughts, what's the very first question we should ask it?
This is for entertainment purposes only.